Today we're going to look at how to model a sinusoidal function from a given data set. The process for modeling is going to be a little bit different than the process of graphing when you're given an equation. When we're given an equation, we often look at it as a sine omega x minus phi close parentheses plus b. But when you're modeling, it's actually going to be a little bit easier to think about that omega being factored out. And so that way when we distribute the omega, instead of actually looking at omega x minus a phi, it's going to be omega x minus omega times phi. And that will kind of make it a little bit easier to use the data set and the model to come up with that phase shift. Now, finding the amplitude in the vertical shift is pretty easy when you're given the data set. You're going to look for your largest value of y and your smallest value of y, and for the amplitude, you're going to find the difference between those two and then divide by 2. And so my amplitude for this model is a 16.1. To find your vertical shift, we're going to find the mean of those two numbers. So let's go ahead and add those two numbers together, divide by 2, and I get a 40.9. Finding omega, again, is a little bit different than what we would do if we were actually graphing an equation. If we were graphing, we would take the omega and we would look for the period, which is t. And so t is 2 pi over omega. But if we rewrite that, we can work backwards and find our omega. So cross multiply, you get t times omega equal to 2 pi. Divide both sides by t, and now my omega is isolated. Given the data set, you're going to be either able to identify what the period is, or you'll be able to deduct that from whatever the storyline is. And so I have 12 pieces of data that are representing an average monthly temperature. So what is a cycle of months but a year? And so here my t is 12. And so for me to find omega, that would be 2 pi divided by 12. And that would be pi over 6. So remember what omega says. Omega says this is how much of one cycle you complete by the time you hit 2 pi. So by the time we hit 2 pi, we won't even have done a full cycle yet, because it's a much longer process. At this point, I'm not going to do anything else to find the phase shift, but I'm actually going to go into the calculator and start to look at what my data set looks like. So I am going to go into Stat, Edit, and in my L1s, I'm going to put all my X's, and in the L2s, I'm going to put all the Y's. I put those in so you didn't have to watch me type numbers into a calculator. And then I'll say second y equals to pull up the stat plot. And your stat plot is probably off like mine is. And so when I hit Enter, the blinking cursor is on the on, and so I hit enter, it moves to there. And then I'll hit my arrow key down and make sure that my scatter plot is highlighted. If you have maybe a different one highlighted, like maybe a histogram, you just want to move that over and hit enter so that's highlighted. It will automatically go to L1 for your X's and L2 for your Y's. Now, when you hit graph, you're probably not going to see anything because you're most likely on a standard -10 to 10 plane. So we're going to have to go into zoom and go down to either Z stat or zoom stat, depending on what version of the calculator you have. And when you hit enter, we have this beautiful partial sine curve, right? And now I can see that I have kind of like that first bump, right? So I start, I hit a peak, I head back down. So now remember that your sine curve is symmetric, and it kind of has 4 parts. So halfway through is where you'll go through the x-axis on your parent function. So you kind of have like the top bump on the first part and the bottom bump on the second part. Halfway through the first half, so at the first quarter, if you will, is where you're going to hit a max. And halfway through the second part, or that third quarter, is where you're going to hit your min. And so if I'm thinking about where my data would be given without the storyline, if I have a cycle of t, halfway through would be 6. A quarter of the way through would be 3. And 75% of the way through would be 9, right? Because this is from 0 to 12, and this is how all sine curves work, that they're always going to be symmetric. So according to the model, my max should be at a 3. That's where I am right now. And I'm going to go into y equals and type in the parts of the model that we have, which is 16.1 sine. I'm going to put pi over 6, and then I'm going to put a parentheses, x, close parentheses, and close another parentheses, which will make a little bit more sense after we find our phase shift, plus a 40.9. And now when I hit graph, it's a little bit easier to see why we need to do the phase shift. I peak here at about 3, which makes sense, but my data says, no, you need to peak over here at 7, and so I need to scoot this over to the right 4 spots. Well, to move something over to the right, then inside here needs to look negative, right? So my 4 is going to go in here. I'm going to come back to my y equals, and inside the parentheses with the x, I'm going to say minus 4. And then I'm going to close my sign, and then I'm going to put the 40 plus 9. And when I hit graph, hopefully it will go the way that we want it to go. Yay, and there he goes. So we have a pretty nice model here, but in all likelihood, you would not see it written like this with the omega factored out if it said, here's an equation, graph me. The way you would see it as if it had been distributed through. And so what they're looking for in a textbook version is that factored through, that it's distributed through. We want the 16.1 sine omega, by omega, which is pi over 6x, but then you're going to need to multiply that omega times that phase shift of the 4. And so 4 times pi over 6 is going to be 2/3, and of course it's still negative because I have the minus sign, plus the 40.9. This is what you would see in a textbook if you were given a model to graph. But when you're working backwards and trying to put that model together, it's a lot easier to look at it as already being separated. So let's see how close we've got using this by hand. If I go back to my main screen and hit clear, I'm going to go stat, over to calc, and I'm going to scroll down till I see sine reg. There he is. It's at C for me, maybe at a different number or letter for you. And when I hit enter twice, it will slowly generate a value. Now it's going to give you values, one, that are irrational, two, it's going to give you the omega distributed through. You see how it says A sine bx plus c plus d. It's not omega times the quantity. So if we want to compare our values, we had our A value was pretty close. This is a 15.7. We had a 16.1. 40.9 for the phase shift. That's not so bad. We had a 40.9. Our omega was a pi over 6. And if I want to look at what pi over 6 looks like, that's pretty close. They had a 5.2 when you round, and we had a 5.2 when you round. But notice that C value is not the 4 that we came up with. It distributes that omega the full way through. So pi divided by 6 times 4 is the 2.9, and of course it's minus because that's a part of the formula. So you can find a surprisingly accurate model using the 4-step method by hand, but the calculator is always going to be a little bit more precise because it takes a little bit more into account when it's finding these values, and of course it doesn't round to the 10th or the 100ths. And so this is how you would model a sinusoidal function by hand and by using the calculator.